Hey folks, I'm currently at LAX waiting to board an airplane to China for a workshop, scientific workshop, and I thought I'd pass the time by recording a video about some more fun, weird mathematics that I love. In this case, the question of how big is infinity and are some infinities bigger than others? This is me continuing some posts on some mind-boggling math that I really love, following up on one that I did about a week ago. And this particular video is based on some blog posts I did a few years ago with the titles, Infinity is Weird. Now, this is actually a question that I asked when I was a kid, probably maybe like 10 years old, and I wondered if some infinities were bigger than others, and my reasoning was there had to be, because you can imagine hypothetically an infinite number of planets, and then you think to yourself, well, each of those planets is made up of a finite but very large number of atoms. So there's always more atoms than planets, right? So by my reasoning, there are some infinities bigger than others. My conclusion was right. My argument was wrong, as we'll see. So in order to answer this question, we have to talk about how we can actually measure the size of sets, and in particular, the size of infinite sets of things. The analysis of this goes back to the late 1800s and was first done by a German mathematician named Georg Cantor, who basically formed the foundations of what we now call set theory. So what is a set? A set is usually just, roughly speaking, a collection of objects grouped together by some unifying theme. Like if we talk about numbers, we could talk about the set of even numbers that are less than or equal to 10. We could talk about the set of prime numbers that are less than 20. We could talk about sets of, apples that we own, things like that. Now we can extend the idea of sets to infinite sets, such as the natural numbers or the counting numbers, 1, 2, 3, 4, 5, on and on and on endlessly. And that is clearly an infinite set. We can always find another whole number bigger than the last. But then you can ask a question like, is the set of even numbers 2, 4, 6, 8, 10 all the way up to infinity smaller? You might think so based on the planet argument I made earlier, but we can actually show that that is not correct. So how do we compare sizes of sets to figure out which is bigger, especially when we're talking about infinite sets? Or how do we determine, as it's known, the cardinality of a set? As a practical example, imagine we have a stack of M&Ms. We want to split that stack of M&Ms into two equal or as close to equal stacks as possible. How could we count them and make sure those two stacks are equal? Well, the naive way to do it is we first count the whole stack. We have 12 M&Ms. And then we count on exactly 1/2 of each stack so that each person gets 6 M&Ms. This is a rather impractical way to do it, though, especially if you have a really, really large bag of M&Ms or an infinite bag. An alternative approach is we start with the whole stack, and then we just line up one M&M next to another. We keep doing that until we've got two stacks that are equal. This approach is far more practical, especially if we don't want to know the total number of M&Ms. We just want to make sure that the stacks are equal, or we want to assess whether one stack is bigger than another. And this works for infinite sets as well as finite sets, and it's called establishing a one-to-one correspondence. As an example of one-to-one correspondence, imagine we take the set of natural numbers, 1, 2, 3, 4, 5, on and on, and we compare it to the set of natural numbers plus one extra element that we just call A. Well, we can still establish a one-to-one correspondence between these two sets because we connect A to 1, 1 to 2, 2 to 3, and we do this on and on and on, and in principle we can do this infinitely. We therefore conclude that, in fact, those two sets are the same size. Or to put it colloquially, infinity plus 1 is equal to infinity. We can also argue roughly that infinity plus infinity is equal to infinity, and imagine that we have two sets of natural numbers. One is primed and one is unprimed. And we say, which set is bigger, the set of natural numbers or the set of two stacks of natural numbers together? And in fact, again, we can make a one-to-one correspondence. We can do 1 to 1, 2 to 1 prime, 3 to 2, 4 to 2 prime, and so on. And we can just do this endlessly, so we can effectively argue that infinity plus infinity, when talking about the natural numbers, is equal to infinity. I might say that this argument sounds very non-rigorous and very loosey-goosey. We can kind of make it more rigorous or see the rigor by turning things around and saying, for instance, if we look at the natural numbers and the even numbers, we can point out that for any even number you give me, I can tell you what natural number matches to it, and vice versa. And so if you don't think that one-to-one correspondence shows these two sets are the same, you've got to be able to find one number in one set that does not match the number in the other set. And actually, this will turn out to be important in a later post. Now we could go even further and we could ask, is infinity times infinity equal to infinity? And in this case, we're talking about the natural numbers again. If we basically look at the set of natural numbers times the natural numbers, is that also just equal to the size of the set of natural numbers? And the answer is yes, and the clever way we do it is we arrange the numbers on a grid. We have horizontally one set of counting numbers, vertically we have the other set, and then we draw a line, and we show that we can draw a line, as on the right, that runs through all of those pairs of counting numbers. So we're able to show that pairs of counting numbers, or infinity times infinity, again can be put into one-to-one correspondence with the natural numbers themselves. So infinity counting number times infinity counting number equals infinity counting number. And as I alluded to earlier, we can put the even numbers in one-to-one correspondence with the natural numbers, therefore demonstrating that the two sets are of the same size, of the same cardinality. This incidentally shows why I was wrong as a kid about the sizes of infinity, because the comparison of the even numbers to the natural numbers is comparable to what I was saying about the number of atoms and the number of planets. Turns out that we still can, in both cases, number of planets and number of atoms, we can line them up, or we can count them. And because we can count them, they're both of the same infinite size, equal to the size of the counting numbers. Things start to get more profound when you say, what is the size of the set of prime numbers, and how does that compare to the natural numbers? And again, we can put them in one-to-one correspondence. The two sets are the same size. Well, what can we say about the rational numbers, which are a fraction divided by a fraction? Well, it turns out we can use the same trick we did for infinity times infinity. We can write all the rational numbers basically as a set of horizontal counting numbers and a set of vertical counting numbers. We can throw out those elements that are redundant, that match with previous ones, but again, we can put everything into one-to-one correspondence with the counting numbers in a systematic way. So the first stage of our infinity journey says that there are a lot of sets of infinity that you would think would be of different sizes, but are of exactly the same size. If that were the whole story, then that would imply that all infinities are the same size, and that would be pretty boring. But in an upcoming post, we'll demonstrate that some infinities are bigger than others, and things just get weirder from there. Stay tuned.